Hello, welcome back. So in class, we described a system undergoing boundary work. And maybe the idea would be you had a piston assembly, there's a piston head, and the system is the stuff inside. Sorry, the system is inside the piston, and in response to adding heat or maybe external forces or whatever, the volume of the inside the piston will change. So we derived in class the following expression that the work, and this is the work by the system, right? Remember what we're calling positive work is work by the system. So think of it, a good car engine will produce work, useful work, and so that's going to be a positive number for us. Production is positive, okay? And what we had in class was that this was given by the integral of P dV, where the pressure, I write it this way, but this in general is not constant. In general. And so, so you kind of, even though the variable dependence is oftentimes suppressed, you can't just pull that out and say it's equal to P delta V. That's a very special case and not usually correct. Let's think about this from a different point of view. And what I'm going to do is think of it graphically. So graphically, we can make a PV diagram. And so if I do that, and I get something like this. So let's say that I've got some curve. Let's say, well, let's think about an ideal gas. At constant temperature. And we'll make it a closed system so we aren't losing particles or anything like that. Well, we could use the equation of state to say PV equals mRT. Remember, an aside in my aside, R is R bar over the molecular weight. And R bar is the number that you learned about in chemistry, 8.314, I believe. Okay, so this is the form of the ideal gas law that we will use in this course. And if temperature is constant, and mass is constant if it's a closed system, and R is a constant, that just once you know the type of gas, then you have that number. We see that pressure isn't going to be constant. In fact, the pressure times volume is a constant, or turning around, we learn that P is mRT over the volume. Okay, this is one example. So then I can go back to my definition of work, or so I can kind of plot this out. So what that means is there's some constant, but basically it's something like this. Sorry, should be like a 1 over x kind of curve. It's terrible. Well, all right, you guys are used to it by now, hopefully. All right, so what you find is that this curve describes situations of constant temperature. So if we had a process which took us from one state to another state, so from small volume, high pressure, to large volume, low pressure, we could evaluate the work. The work is the integral of P dV from 1 to 2. That's the integral of mRT. Those are just constants for this, because remember, we're assuming it's isothermal. V dV And doing that integral, I get mRt, natural log of the final volume divided by the initial volume. All right, using some properties of logs there. All right, now, this prefactor is always positive because this temperature must be an absolute temperature. We're using Kelvin, or we're using IU gas law. What about the change in volume? What do we notice? Well, we know that V2 is larger than V1, therefore the ratio is bigger than 1, which means the logarithm is positive. This is a positive answer. And indeed, graphically, what we can interpret this work. Work is given by this integral, but it's nothing other than the integral under the PV diagram. So the area in the PV diagram gives me the work by the system. So if state 1 is here and state 2 is here, what we usually do is we actually write this with this process with an arrow. I should have done that, but I just forgot. Usually, even though it was clear because it labeled them 1 and 2, but there'll be other times where it's not so clear. And when we draw these curves for the process, this would be an isothermal process taking me from state 1 to state 2, we put a little arrow on it. And if you are integrating the right way, you get a positive area. And if you're integrating backwards, you get a negative area. Okay. So this region would correspond to positive area, which is equal to or equivalent to positive work. It's like the power stroke in an engine or something. Whereas you could have other systems, for example, what if you had the gas and you ran it through a compressor? That's going to squeeze the gas, and so it'll start out really big and low pressure, and it's going to finish over here at some V2, and that, if you think of it from an area point of view, it's like you're integrating backwards. And so, so here you have a negative area. And sure enough, if you think about it, when you run the gas through a compressor, it's not producing work, it's consuming work. So you end up with a negative work. So the area under a PV diagram gives you the work performed, and the direction of the area, the minus sign of the area, the way that you're integrating determines the sign. One last little thing is we can also have processes, like we can have something where it's like two processes put back to back. You could have state 1 here and state 2 here, and you could have something like this. Maybe change colors, use the magic of color. You could have a process from 1 to 2 going this way, followed by a process, I don't know, let's choose something different, 2 to back to 1, like that. And what you would have is, well, okay, so first off, this is called a cycle, because this means that you went around from one state to another state and then back. So that means when you've gone around one time is completely equivalent to the starting point. So that's an interesting thing. All properties must come back to themselves when you have a cycle. I'll have more to say on that in a later video. But as far as the work done, what we would have here is, well, you would integrate on the forward path and then on the backward path. So that would look like this. The forward path would give me, a green contribution, which is positive. So the work, the total work, or work net, sometimes it's called, or sometimes it's called the cycle work, in this case because it's a cycle, equals the green area. And then, oh, you got to think about what you're doing. The second part of this trip is going to be you're integrating backwards. So it'd be the positive green area, and you'd actually subtract off the lower blue area because you're integrating backwards. And what you find is that the region in the middle, how can I do that? Well, we'll just try this. The region in the middle gives me the network. So the area between the curves. I should have said that. Customarily, we always put pressure here. Well, we put volume at the bottom, customarily, whenever that's a relevant variable. So the area inside the curve gives you W net. Okay, so from a PV diagram, that's how you can interpret these integrals that we have been talking about. All right, that's all for this video. I'll have more later.